Hello everyone, this is Brock Skaggs, and I'm going to make this video where we'll look at the same gear train problem that we looked at in a hand calculation before, except for now we're going to actually model it up in SolidWorks and see if we can use SolidWorks Motion to evaluate the performance of the gear train. And more specifically, we're going to basically set the pinion here on the far left to be traveling at 720 RPMs in the counterclockwise direction for its angular velocity, and we want to know the angular velocity of the output gear, gear number 6 here on the far right hand side of our train. And so we've already done the calculations by hand here that you can see below in order to figure out the output angular velocity, and that's in black here, the omega 6. We're expecting it to be roughly 98.18 RPMs in the clockwise direction. And we also did some center distance calculations here in blue that'll help us set up our gear model there, or gear train model itself. And so with that being said, let's go ahead and hop right into SolidWorks. And so getting into SolidWorks, this will be an assembly, and so we'll start here. And the first thing I'm going to do instead of bringing it apart is go ahead and show my planes. And then I also want to show the axes and the temporary axes here. And so with this, I'm going to be using the SolidWorks toolbox in order to bring the gears in eventually. But before I even do that, I'm going to create an axis. And so I'll just go from reference geometry down to axes. And I'll use the intersection of the right and top planes to define this axis 1 here. And so this axis 1 here will be the axis of revolution for the little spur gear on the far left hand side. And so to obtain the spur gears, what I'll do is come over here, and I've already got this popped out, but basically I'm working through the toolbox here, not the design library, but our SolidWorks toolbox. And I'm going to go down to ANSI inch for the standard. I'm looking for gears, so that's in power transmission. And then under gears, there's a bunch of different types of gears, but I'm just looking for external spur gears here. And so I'll just drag and drop at this point. And so here it is. There's a spur gear, and now it's time to configure it. And so if this is the little pinion gear, I'm going to leave off the hub this time, but the diametral pitch here is 6, and so diametral pitch is 6 is good. The pressure angle is 20 degrees, which is also good. And N1 is 18, so the number of teeth needs to be 18, so I'll slide that down to here. As far as some of the other values that you would need to completely describe the gear, I'm using a face width of 1. I'm using none for the hub style, nominal shaft diameter is 1, and no keyways here. And so here I'm just really interested in the kinematics of it all, so I'm leaving a lot of this stuff bare, if you will. I'm just accepting the defaults. And so there's the first little gear. I'm going to right click on it and float it to give it back its degrees of freedom. And let's go ahead and rotate this guy around so it looks a little better. There we go. And so now this thing should be able to move around in space. I'll start mating it up now, so I'll mate this axis to the temporary axis, which is good. And then I'm going to mate this front plane to the back face of the gear itself here. And just with those two mates, what I should have at this point is a nice little gear that rotates about that axis. That's the only degree of freedom that thing should have left at this point, is to be able to rotate about the axis. I can't slide there because of our coincident with the front plane, which is good. One thing I am going to want to do is set an initial position. So I'll just use, say, this plane here, plane 2 of the gear, and I'll mate it with the top plane of the assembly for coincident 3. Now this thing should be fully locked in space there, so it can't rotate. And I'm going to rename that coincident 3 mate to be initial position here. That way when I have a bunch of different coincidents here, that one will stick out and I can just come back in and suppress it just like so in order to spin the gear here and have it interact with the rest of the gear train. And so I've got the first gear in place. So what about the second gear? Well, the second gear here, gear 2, it's going to have 44 teeth, same diametral pitch and pressure angle, but how far do I space it apart? Well, that's where these center distance calculations are going to come to play. And so here I've got a center 1, 2, and it's 5.16, and the 6 repeats there is the correct center distance for us. And so the way I'm going to do that is by first starting to create a plane. And I'll just space it off 6 inches is fine. And then I'll extend this plane out. And so now I've got an intersection of two planes, and I'll create an axis with those, just the way I did before. And so axis 2 will be where I want this gear to be rotating about. The only problem is right now it's 6 inches apart and it needs to be 5.16. And so the way I'm going to do that is I'm going to use some variables to store all that in. And so that's in Tools, drop down for Equation for the global variables. And the first one we'll have is C_12. The value or expression. Here, instead of typing in 5.16, I'm going to type in the expression 18 plus 44 over 12. And so here, for my value is 18 plus 44 over 12, and let SolidWorks do the math, and you can see it evaluates to 5.16 repeating there. And so the nice thing about this is now I can save this as a global variable. You can see it up here in the equations folder that now is there. And now I can use this to drive the distance of plane 1. And so by just double clicking on plane 1 in the graphics window, it pulls up that dimension you can see as 6. I'll double click on that now. It brings up the usual driving dimension dialog box. I'm just going to type in equals and then toggle down into global variables, and there is my C12 global variable that I can now reference. And so now when I reference that, it should move it a little bit closer as I update there, and you should have seen it slip in there. And so now it's just a matter of getting that gear. And so the gear, diametral pitch of 6, 20 degrees is the pressure angle, and 44 teeth on it. And so we'll go right back here to this. I could go through here and drag off, or I can just create an instance here. Let's just create an instance. I'll select, hold Control down, and now I've got my second gear instance. And so now we'll have to just configure it. So I'll right click, I'll go to Edit Toolbox Component. Notice a lot of the values are already kept for us. Diametral pitch and pressure angle are good. And so now I just need to come in here and change the number of teeth to 44. So you see a much larger gear is then created. That's looking good. And so it's just a matter of mating this thing up again. And so I'll use axis to the temporary axis, plane to plane. There we go. And so now it should be able to spin about that axis 2, as you can see. And what I'm going to do is I'm just going to kind of eyeball it for now and get it to where these teeth look like they're matching up. And so the next thing I need to do is connect these two. And so that when I spin the one on the left, the one on the right spins appropriately. And so the way I'm going to do this is using a specific sketch. And so if I open up the gear part, there's a feature called Tooth Cut. And inside of Tooth Cut, there is this Tooth Cut sketch. And so I'm going to show that. You can see the sketch geometry there. And then inside of the other larger gear, I'm going to do the same thing and show its tooth cut sketch. And so one thing you'll see is there's one reference geometry circle here that represents the pitch circle of the gear itself right there. And then this one is the pitch circle right here. And what you should see is that they should become basically tangent when we're at the correct center distances there. And I can actually use those as references to drive a gear mate. And so gear mates are mechanical mates, and so we go to mates, not a standard mate or advanced, but actual mechanical mate. And you come down to gear. And so there's a few different ways to define the velocity ratio between these gears. But one way that's fairly convenient is just to select the two sketch circles associated with those pitch circle diameters and let those drive the gear ratio. And so I'll just accept that. Come down here and now suppress my initial position, and you'll see what happens when I move the one on the left. The gear on the right behaves just as we would expect here for these mating spur gears. And so that's just a very nice interaction that we're able to get very easily with SolidWorks. And so with that put in place, now we just start adding to our train. And so I'll go back to one note here. I've got gear number 3. It has 52 teeth. And so I'll just create another instance by dragging off while holding control. Then I need to configure again. We said this one had 52 teeth, so a little bit larger. Accept it. And now it's ready to mate that one up appropriately. And so you can see here, the idea is gears 2 and 3 are lying on the same shaft, so they should carry the same angular velocity. And so the way we'll do that is use the temporary axis and axis 2 to mate that together. I'm going to use this front face and the front plane to bring it together here, eliminate the sliding in the Z direction. And then finally, I'll use a couple planes associated with the gears themselves. And so I can take, for instance, the plane 2 from my second gear and mate it with plane 2 of the third gear. And so they are going to become coincident. And so what should happen now if I test my small little gear train here is that gears 2 and 3 should turn together, as you're seeing there as I turn the pinion. And so now we really need to just keep expanding this out to create the rest of the train itself here. And so what I'll do, we need to define another center distance, right, for the axis of 4 and 5 gears. And so that is center 3, 4, and so it's 8.6 repeating, or 52 plus 52, 104 over 12 essentially is the fraction. And so I'll create another global variable. We'll call this C underscore, I believe it was 3, 4. It's 52 plus 52 divided by 12. Okay. Same method here, except we're going to use this plane here, plane 1, as our reference. And so we'll go reference geometry here. We'll just accept the default 6. Then I'll come back in here and adjust. So now this is going to be equal to C34. Rebuild, and you can see the plane jump out there. And now a matter of creating the axis again. And so we'll go from reference geometry axis, plane 2, in the top plane. There's axis 3. And now to create our next gear. And so that's gear number 4. Notice gear number 4 has also 52 teeth, so it's the exact same thing as gear 3. And so I'll just hold control off. This is a copy of gear 3 now, and mate it up just as we've been doing. So axis to temporary axis, this face here to this face here. And so we've got front plane to the face of the gear. And now we're ready to apply our gear mate to link this thing together. And so here again, I'm going to position it so that the teeth don't interfere. And I need to show some sketches again. And so here, I'll go ahead and show the tooth sketch of my third gear. And now of the fourth gear, drilling down and doing the same thing as well. Or I guess they're the same exact gear, so it picked it up automatically for us. And now for our gear mate. And so from mates, mechanical mates, gear mate, and then select the 2 reference circles, which are there to be the pitch circles of the gears. So that's looking pretty good. And then I will test by suppressing my disposition. I turn my pinion on the left, and you can see the interaction there. So looks like things are going appropriately. And unsuppress. So a few more gears, so I'll do it rather quickly now. We're on gear number 5. It has 20 teeth, and so I'll just create another copy. We'll configure it. It's going to be a much smaller gear here. And so coming down to 20 teeth. And then we'll mate it very similar to the way we did the second and third. And so here, axis to temporary axis. Now front plane to the back face of this gear. And then we've got to link the larger gear and the smaller gear together so that they have the same angular velocities. And so we can take, for instance, the plane 2 from the small gear and mate it with plane 2 of the larger gear there. and rebuilding, and there we have it. And one more gear, gear number 6. And so first we got to create that center distance again. And so 1/6 is, or excuse me, 5/6 is 6.6, so 80 over 12. And so again, creating the global variable first. 80 over 12 is the center distance. And then we'll create our plane based off of the last plane that we created, so plane 2. Adjusting the dimension at this point so I can reference now the global variable. Extend out the top plane so we can see it a little better, creating the axis of revolution at this point, and then bringing our gear in. So I'll just grab the last gear I put in, pull it off, and gear number 6 appears to have 60 teeth. And so we'll configure this gear at this point. So edit the toolbox component, 60 teeth. Gets us to here. And now just a few mates. And so mate axis 4 to the temporary axis. We'll mate the front plane of the assembly to this back face of the gear. And then one gear mate now. And so at this point we'll go to front view, make sure that these gear teeth don't intersect. We need to show a few sketches. And so there's for the smaller gear. Again, we're looking at that tooth cut sketch. And then for the larger one here, there's that as well. And then we'll go straight into mates. We want a mechanical mate, the gear mate, and again I'm selecting the sketch circles associated with those pitch circles for the gears. And that's looking good. And so at this point I'm going to do one last test. Now I'll suppress the initial position. Let's go ahead and hide all the planes, hide the axes and the temporary axes so we can see a little better. Also need to hide the sketches, they're no longer needed. And so now when I move the pinion here on the far left, you can see the motion there. And so that looks quite appropriate, if I don't say so myself. Looks like everything's functioning fairly well. Alright, so I'll go ahead and unsuppress the initial position. And we can now go into the motion study. So at this point we are trying to figure out if I spin this guy on the left at 720 RPMs in the counterclockwise direction, how fast does the one on the right here spin? And so first thing I'm going to do is go to the add-ins and make sure I have SolidWorks Motion added in, which I do. Now I'll just go straight into Motion Study 1. I want to pull data off of it, so I'm going to go down to Motion Analysis for the study type. Also in my mates, I'm going to go ahead and suppress the initial position to give this thing back its rotational degrees of freedom. Finally, we can put a motor in. The motor goes right here. I like to put it right on that cylindrical face because it attaches it to the actual body itself, so the small gear here, and also gives it an axis in order to rotate about. Here we want it to rotate in the counterclockwise direction, so I'm thinking about looking in this orientation, so we'll flip the direction, and we wanted 720 RPMs here. It doesn't really matter the amount of time here, just a constant angular velocity that we're looking at, and so with any luck we should be able to now just hit calculate and have it run for us. So there it is. You can see it play back here a little bit. Here I don't really like the graphics that I'm seeing, but we'll see what the data looks like. As far as the graphics go, one thing we can do is slow it down a little bit here, and you can see that although these two gears here should have one and the same angular velocity, you can see actually the nearer one here is actually going in the counterclockwise direction, and what appears to happen is the back one's rotating against it in the clockwise direction. This should really happen because of the way the mates are set up between those, but it's showing in the graphics window there. And so I'm not real thrilled with that, but let's check and see what the angular velocity of this wheel looks like. And so here we'll go down to displacement velocity acceleration. I'm looking for an angular velocity. I need it to be about the z component, just the way these things are set up. And if I click this inner cylindrical face, Let's not pick that face because it just has the points. Let's click the face here. There we go. And here's the value. And so it's saying that that gear is rotating at negative 589 degrees per second there. And so the negative generally is considered clockwise motion in this effect. So that makes sense to us since we wanted clockwise motion here. And now we just have the conversion between 98.18 RPMs and negative 589 degrees per second. And so what I'll do is I'll just hop into Excel. My hand calculations set around 98.18. That was in degrees per second, so degrees per minute would be 1 minute is in the denominator, so we'd have 60 seconds, so I'd multiply this by 60. And then I need to get to revolutions per minute. Well, there's 360 degrees per revolution, so I'd take this and divide it by 360 to get to 16 point. I think I've messed up at some point here. Let me think. So we've got 98.18. Oh, excuse me. This is RPMs. That's where we're at. This is RPM, so we did it exactly backwards. My apologies. And so RPMs, and so this is revolutions per minute. And so we could first get to revs per second. Here, this is revs per minute. There we go. And so here, 1 minute. And so this needs to be divided by 60 to get revolutions per second. And then we'd have degrees per second, where there's 1 revolution per 360 degrees, so times 360. My apologies there. And so you can see 98.18 RPMs is roughly 589 degrees per second, which is exactly the magnitude that SolidWorks is putting out here. You can see 589 degrees per second there, and we're taking the negative sign to mean clockwise rotation, which is exactly what we were saying here in our hand calculations. And so these are agreeing quite well with the SolidWorks result that I'm seeing from the plot. I do have a little bit of an issue with the way things are rotating inside of the graphics area, but I do agree with this value for the output angular velocity, so that is good. And so I think that's enough for this video. Basically, we went through and used a SolidWorks motion model to help validate our hand calculations here for this gear train. And so, as always, thank you for watching the video, and hopefully this helps you out with using SolidWorks Motion in order to do some kinematic modeling. Thanks again.